Hello and welcome. In this video, I want to take a look at the notion of divergence. Um, it is both a concept that we have in 2D or in 3D or even higher dimensions if you want. Here we go. Definition: if F is a vector field, P comma Q, in R2 and P sub x and Q sub y both exist, so partial P with respect to x, partial Q with respect to y. Then we define the divergence as the divergence of the vector field F is px plus qy. Right? So partial of p with respect to x plus partial of q with respect to y. Likewise, in R3, if the vector field is pqr with the partial of p with respect to x, the partial of q with respect to y, and the partial of r with respect to z all existing, then the divergence of F equals partial of p with respect to x plus the partial of q with respect to y plus the partial of r with respect to z. Okay, so let's just do a quick example here just to see the calculation. So here's a random vector field. So the vector field is here in 3D. The first component, x times y times z. The second component is x plus y plus z. And the third component is x times y divided by z. The divergence is, I'm going to take the partial of this first one with respect to x, plus the partial of the second one with respect to y, plus the partial of the third one with respect to z. So the first one with respect to x is just y times z. Second one with respect to y is just 1. And the last one with respect to z, this is a z to the minus 1, so I get minus z to the minus 2, but that's still times xy, so xy divided by z squared with a minus sign out front, and I'm adding those all together. So the divergence is yz plus 1 minus xy divided by z squared. Notice, this is a scalar function that you give me an xyz, and I'm going to do this calculation. I'm going to multiply y times z, I'm going to add 1, and I'm going to multiply x times y and divide that by z squared, subtract it from what I had before. Right? This is a scalar. This is a number that comes out of this. So your input is a vector field. Taking the divergence gives you a function, a multivariable function, in this case 3 variables, but its output is a number. Now, I want to take a look at some notation here. In many textbooks, you're going to see the divergence denoted this way. It is quite often called del dot f, that this upside down delta is quite often referred to as del. Right? Now, we do this thing where we consider this symbol del as representing the vector, and I put that in quotes because this isn't really a vector. It's an operation that looks like and behaves like a vector. So I'm just writing this. It's a vector with the first component being the partial with respect to x, second component is the partial with respect to y, and the third component is the partial with respect to z. Notice, I'm not saying what you're taking the partial of, it's just that that's essentially an operator waiting to have something done to it, or to do something to something else here, right? So del is this vector. And so the expression of del dotted with f can be seen this way. Del is this vector, f is this vector, pqr, and when you dot the two vectors together, you multiply the first components together, you multiply the second components together, you multiply the third components together, and you add them up, right? So you'd get the partial with respect to x times, and again, I'm going to quote that because it's not really times, it's partial with respect to x of p, and the partial with respect to y of q, and the partial with respect to z of r, and add the results. That's exactly what the divergence is. So the use of this notation, I see it like back in Calc 1, we had two different notations for derivatives. We had the prime notation, right? F prime or y prime, however you want to write that. And we had Leibniz notation, dy, dx, and whatnot. And the Leibniz notation is really superior because dy divided by dx looks like a fraction. It looks like a slope, change in y divided by change in x, which is exactly what the derivative is. So the notation looks like and behaves like what the concept is that you're working with, that the notion of derivative is a change in y over change in x. It's a slope. And so the notation looks like this. This del operator is sort of behaving like a vector, so we write it like a vector. And I should point out that we've used this same symbol before to denote the gradient, and it works in that way as well. If you think of del as a vector and f as a scalar function, we know how to multiply vectors times scalars, right? You just multiply the scalar times each component. So this vector times the scalar function f is just the f gets multiplied into each component. So you get partial of f with respect to x, comma, partial of f with respect to y, comma, partial of f with respect to z, which is exactly what the definition of the gradient is. So del, this thing here, it's not a vector. It is an operator that operates in a couple different ways depending on how you use it, right? In taking the gradient, we're multiplying it, again, multiplying in quotes, or applying it to a scalar function. And for the divergence, we are dotting it with a vector field. Each way, each time, there's some operation being applied to either a function or a vector field. And it's very nicely represented by that vector with those partial derivatives in it. So I'm going to give you here a few examples of divergence of vector fields that I think are sort of the stereotypical ones. Want to see what the divergence is actually telling you, right? That just the standard f of xy is x comma y. So at every point you got the vector, you know, if you're from the origin out to that point, well, that's the vector that you're going to put at that point. Again, this is drawn with the vectors shrunk down substantially, but the vectors are all pointing away from the origin. Right? Things are diverging. Definitely, things are going outwards. The divergence, partial of the first one with respect to x is 1, partial of the second one with respect to y is 1, 1 plus 1 is 2. This has a divergence of 2 everywhere. No matter where you are, it is 2. Now I have this, I think I have this live. So if this is CalcPlot 3D. And one of the things that that CalcPlot 3D does here, when I have this just looking in the 2D world, I can click on a point, and this is going to show me the divergence at each point. Now, it's not, there's some weird things going on, but down here I can see that the divergence is 2. When I click over here, the divergence is 2. And, you know, everywhere I click, it's saying that the divergence is 2. It's a constant divergence. Now, I'm not entirely sure what this circle and these little green vectors are showing me. I think what they're showing me is essentially, because all the little blue vectors have been scaled down, they're showing me the vectors in their full length at a circle around whatever point I'm clicking on. And what I notice is that it looks to me like this circle, whatever diameter they've chosen here, is being sent to a circle that's twice as big. So at least it's showing me things are expanding, right? That this is, the vector field is diverging. Right, so that's that one. It's as I say, I'm not entirely sure what those green what that all is telling me. The divergence has not, it's not those vectors. The divergence is just a number. And in this case, the divergence seems to always be 2, right? So we calculate it. Right, so here's another one. Just turn all those vectors around. Now everything's pointing towards the origin. So the partial of the first one with respect to x is -1. Partial of the second part with respect to y is -1. And I have a divergence always equal to -2. Right? And in this case, we should see that everything is headed into the origin. And I think of this as negative divergence or convergence, right? Things are getting shrunken together. Oops. I need to switch this to show me the divergence at any point. And this one, again, this is where it doesn't make a whole lot of sense to me, because this vector field is set up so that at any point the vector being assigned there is exactly the right length to point directly back to the origin. So this circle is going down here. It's like, is that, it's not zero. The divergence isn't zero at any point. You can see down here that divergence is -2 everywhere. So like I say, I'm not entirely sure what that, what those little green arrows are showing me, but at least it's showing the calculation. So there was one with positive divergence where things seem to be getting further apart. Negative divergence, now we're getting closer together. Vector field's kind of squeezing in. The next one is just rotation. So f of x comma y is y comma minus x. Partial of the first one with respect to x is 0. Partial of the second one with respect to y is 0. And 0 plus 0 is 0. So this has 0 convergence everywhere. And if I do this little thing again here, at least the number down here is saying, yeah, look, it's 0 over here, it's 0 over there. But here, I'm not sure, right? Because it seems like those little green arrows are pointing to a circle that's pretty much the same size, maybe as the one that I started with, right? Maybe slightly bigger. But yeah, somehow that's divergence 0. So again, this is why I don't know what those green arrows are telling me. Back here. Now, it's not always the case. In fact, the very first example we did, it's not always the case that the divergence is a constant. Right? We saw one already. Here's another one where f of xy I have as x minus xy comma minus y plus xy. The divergence, or del dotted with f, I rarely use div of f like the book does. I choose this gradient, this del dotted with f. So anyway, partial of the first with respect to x is 1 minus y. Partial of the second with respect to y is minus 1 plus x. Add those together, the 1 and the minus 1 go away, and I end up with x minus y. Right? So at any point, the divergence is your x component minus your y component. That sometimes is going to be positive and sometimes is going to be negative. So if x is bigger, then it'll be positive. If y is bigger, it's going to be negative. So if I take a look at this one, okay, again, I'm going to do it. I'm going to show this. Over here where the y's are bigger, I'm getting negative divergence, and over here where the x's are bigger, there's positive divergence. And as you move this around, there's spots in the middle here where the divergence is 0. All sorts of odd things that those vectors are doing, but at least you can see that calculation down there as to, I've got a negative divergence over here. Things are squeezing in together, but over here, things seem to be getting farther apart and the divergence is positive. Okay. There's up here where there's this sort of whirlpool going on here. On one side you got negative divergence, and on the other side you got positive divergence. Okay. Now, the divergence is very closely related to a subject that we had in the previous section, and that is source-free fields. Remember, when we were talking about source-free fields, we were talking about the flux integral, and Green's theorem for the flux integral, if you're integrating around a closed loop, it says that it's equal to the double integral of the partial of p with respect to x plus the partial of q with respect to y. That's precisely the divergence. Green's theorem is, the flux version is that the line integral around a closed curve of the flux is equal to the double integral of the divergence. And if that divergence was equal to 0, if partial p with respect to x plus partial q with respect to y is equal to 0, then it was source free, right? That around any loop you're going to have a flux of 0, and so there's no sources, or there's equally many sources as sinks in there, but because it works for every curve, you can say that there are no sources or sinks anywhere. This is source free. Okay, and the theorem is that if F is a continuous vector field where P and Q are differentiable on a simply connected region, then the divergence equaling 0 is equivalent to saying F is source free. Yeah, it's just nice to have a name for that thing, right? That piece of x plus q sub y is the divergence. And we're going to have a similar theorem in 3D coming up in the next couple of sections. It's going to be called the Divergence Theorem, and it'll relate a triple integral of the divergence to a surface integral over the boundary of that 3D region. But anyway, that's coming up in a couple of days or a couple of weeks. Anyway, there you go. There's the notion of divergence.